After we now understand why the Laplace transform is so relevant for everyday engineering work, I will now answer the question of how to find the impulse response of a system by using the inverse Laplace transform, why it's so important, and which kind of information about your system you can extract solely from its response to an impulse excitation. Now imagine again the wheel axle that runs over a small bump, which introduces an external force into the system. In this way, we have a dynamical system that experiences an impulse excitation at the input, and we're interested in its response over time, so the impulse response. We will determine this in 4 steps. First, we derive the transfer function g of s from the equation of motion, which is g of s is equal to z of s divided by f of s is equal to 1 divided by ms squared plus ds plus k. Second, we define the input signal in Laplace form. In our case, it's a perfect unit impulse, a Dirac impulse, delta of t, and Laplace transformed. According to the standard Laplace table, the input signal in Laplace form is simply 1. Now we rearrange the transfer function in order to obtain the next step. Third, we determine the system response in the Laplace-domain, which is g of s multiplied by the input signal. And fourth and finally, we need the system response in the time domain. To achieve this, we have to transform the system response z of s back into the time domain, and we proceed as follows. We have to rearrange z of s into a standard Laplace form such that it can be inverse transformed. According to the Laplace table, you can see a short snippet of such a table here. In that table, you observe the correspondences between functions on the frequency domain on the right-hand side and their corresponding inverse transforms on the time domain on the left-hand side. Now we first divide the equation by m and obtain the following expression. 1 divided by m times 1 divided by s squared plus 2 capital D omega 0 s plus omega 0 squared, where I've replaced d over m with 2 times capital D omega 0 and k over m with omega 0 squared. Next, we perform one further transformation step using the binomial formula and obtain z of s is equal to 1 over m times 1 divided by s plus capital D omega 0 squared plus omega d squared. If this step is not clear to you, let me know in the comments and I will go into more detail. Subscribe if you want to learn engineering properly, as it is required in practice, without the necessary dry theory. At this point, we have simply transformed the expression into a standard form, and we can now directly apply the inverse Laplace transform using the table and obtain the system response. Z of t is equal to 1 over m omega d times e to the power of minus capital D omega 0 times the sine of omega dt. This is the so-called impulse response function. It describes the behavior of the system when subjected to an impulse-like excitation. Referring back to our example, the wheel runs over the small derivation, which induces a force impulse through the tire elasticity, and as a result, the system is set into oscillation. The oscillation decays depending on a damping constant delta, where delta is equal to capital D times omega 0. And this value can be directly read from the impulse response function. If the damping were lower, the oscillation would decay more slowly and would lose less energy per oscillation periods. Furthermore, the damped natural frequency of the system can also be directly identified. This is particularly relevant in practice when one wants to determine system properties, for example when testing competing products where the exact parameters can only be determined experimentally. In addition, any arbitrary signal can be decomposed into a sequence of impulses, and by using the impulse response function together with the convolution integral, the system response can be determined. You can find further, more detailed and free chapters in the first link in the video description, including many real-world engineering examples. Have fun with it!